Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over titrations. So what is a titration? A titration basically is a method or a way to determine the concentration of an unknown substance, and the way you do this is by reacting it with this a known substance of a known concentration. So what you're going to do is use the fact that acids and bases react with each other to neutralize each other. So these are neutralization reactions. And often titration is used with acids and bases. So you might have an acid of an unknown concentration. So you react it with a base that you know the concentration of, and you know they're going to neutralize each other. So at the point at which they neutralize, you can figure out the number of moles you have, and then figure out the volume, and then find the concentration or the molarity. So we know that at the point where you neutralize the substance, right, at the point where the neutralization reaction is finished, when you've added enough of the known base to, say, the unknown acid, at that point, you know that the amount of moles of acid that you have in your unknown has to be equal to the number of moles of the base that you added. So this is just what it means to be neutralized, right? So when I neutralize something, I'm adding an equal amount of that another substance that's going to neutralize all of the other ones. So if I have a certain amount of acid, right, if I have a certain number of moles of acid that I need to neutralize, I'm going to add an equal amount of moles of base to completely react with that acid. At that point, the acid has been neutralized. And so here are some key terms that we're going to use in titrations. So first of all, we have what is called the titrand. And the titrand is the unknown solution you are interested in, right? So it's also referred to as the analyte or the analyte, right? Because it's what's being analyzed. But titrand is also used. So this is the unknown solution that you're trying to figure out the concentration of. And then you have what is called the titrant. And the titrant is the solution that you know the concentration of and that you're using to neutralize the unknown solution. Uh, at During a titration, you'll be titrating until you reach a point called the equivalence point. And the equivalence point is the point at which all of the titrand, right, the unknown solution, has been reacted with the titrant, which is the known solution. So at this point, the moles of acid is equal to the number of moles of base. And then finally, we have what is called an endpoint. Now, the endpoint is the point during the titration where it seems that you have finished the reaction because you see a color change. So simply put, the endpoint is the point at which you see a color change due to an indicator that you put in the solution. So you need something that's going to tell you to stop putting in your titrant. Um, so you need something that's going to tell you when you've reached the equivalence point, and that is what we call the endpoint. The endpoint is where the color change happens, and that's the point at which your titration is finished. You've reached the end and you've reached the equivalence point. But we'll talk about whether or not endpoint and equivalence point are the same. So, how do you know if you've reached the endpoint? Right? So, as I said, we use an indicator. An indicator is a molecule that's usually an acid that is going to change colors based on whether it's in its acid form or whether it's in its base form, right? And that's going to be dependent upon what solution it's in, right? It's going to depend on its environment. So it's going to turn colors based on pH, right? So you can this can show you visually when you've reached the endpoint or the equivalence point. So we need to make sure that we pick the right indicator. So here I have a chart, and you can see the different indicators on the chart. We have methyl violet and thymol blue and methyl orange. And you can see that their range of color change happens at particular pHs. So if you look at methyl violet tends to change from a yellow to a violet color within the pH range of like 0 to 1, right? It looks like it's in the pH of 1 range. Whereas if you look at phenolphthalein, for example, which is a popular common indicator to use in titrations, you could see that around the pH between 8 and 10, around pH 9, it's going to change colors from colorless to pink, right? And so if we use this indicator, the endpoint of our titration would be marked by a color change going from colorless to pink or slightly pink. So depending on what indicator we use, we'll see different color changes. And the thing you want to keep in mind is that you want to pick the indicator that's going to change color at your equivalence point, at the point at which you've neutralized your acid. So, excuse me. So as you can see, different indicators are used for different pH ranges. And so you want your color change to happen at the point or at the pH where you have completely neutralized your acid. So you got to make sure you pick the right indicator for that job. And here again is a much larger table. So you can see that there's a large variety of indicators, and you pretty much have an indicator for any range of pH that you're interested in. And so also you can see down here you have what is called the universal indicator, and it's universal because it covers all pH, the whole pH range. So depending on what color it is, you can determine what pH you are at. So that is also an indicator that's used. So let's talk about how you would set up your lab for a titration. So the lab setup requires that you have what is called a burette, and you have usually an Erlenmeyer flask with your unknown substance in it. So in the burette, you put your known concentration, the substance that you know. So in this case, I have a base. So in my burette, I have a base that has a known concentration. Um, and in my Erlenmeyer flask, I have an acid of an unknown concentration. Now, it doesn't have to be an acid that's unknown. You could switch this. It might be a base. So if I have an unknown base, then I'm going to have a known acid in my burette. But in this case here, the acid is in the Erlenmeyer flask here. I don't know the concentration of it, so I'm going to react it with a base that I do know the concentration of. And so in my burette, the burette has markings on here like a really long like test tube that's graduated, or a really long graduated cylinder. And so on the bottom here, we have what is called a stopcock valve. And so it's going to be closed to not allow any of the fluid through yet. But when I turn it, I can turn it to allow the base to be added to the acid in the Erlenmeyer flask. And I can control how much to add. And this is reading the volume. So I can read the volume on the burette, like the starting volume. And then as I'm adding more and more base, I can record what volume I've added when I've reached the end point. So at the end point, I will stop. So here it looks like it's pink. I've added enough So the phenolphthalein indicator tells me I've reached my endpoint. So then I would read the volume on my burette here, and then I would subtract that from the volume I started with, and I can figure out how much milliliters of my known base I added. I can then go ahead and use this to help me calculate the number of moles of base I added. And remember, at the end point, the number of moles of base is going to be equal to the number of moles of acid, right? And so I can start to figure out, okay, now I know the moles of acid. I know the volume of acid I added to my Erlenmeyer flask, right? So in this case, excuse me. So in this case, I can find the molarity by taking the moles of acid and dividing it by the volume in liters. So, oh, sorry. So when you're doing your titration, this is the way that it looks, right? So I have my Erlenmeyer flask. Notice that it's clear down here. So this is my acidic solution. This is my acid of unknown concentration. I have my base in here, and the indicator phenolphthalein will start to turn pink when it starts to become basic, right? So right now it's clear. So then what I do is I open up the stopcock here, and then I let a little bit of my base in, and then I close it, and then I swirl. You're constantly swirling your Erlenmeyer flask. And so you're waiting to see the solution turn pink. And you're going to get to a point when you start, you can go fairly fast. But when you get to a point where you start to see the pink start to form and then it goes away, that's when you want to slow down, and you're going to add little tiny like drops at a time. So maybe one drop at a time, swirl, make sure it's going to turn pink, make sure the pink goes away. It should go away in like 20 seconds or so. If it goes away, then you add another drop. And then what you'll see is as you get closer and closer to the end point, that pink color will start to last longer, right? So it'll, it'll, you'll start to see the pink grow larger and larger, but then it'll go away as you swirl. And you're waiting until you get to the point where you get this very light pink and it doesn't go away. And you want the pink color to last at least 20 seconds, right? And so, one thing you can do to help you see the pink color, excuse me, is put a white sheet of paper or some white background underneath, usually a white piece of paper or a paper towel that's white underneath, so that way you have a white background by which you can more easily see the light pink color. And what you want is a very, very, very light pink color that's going to last, for 20 seconds or so or longer. Once you get that, you're done. You want to stop. You don't want to add any more. At this point, if you were to add just a tiny fraction more, you would probably turn to a bright pink color as you see in this last Erlenmeyer flask. You can see that the Erlenmeyer flask is very, very pink. That's too far. We don't want a bright pink color. We don't want a dark pink color. We want a light pink color. And so that's the way you do your titration. So you want to make sure you go very carefully, very slowly, so you don't overshoot or go past the endpoint. So once you get to the endpoint, you now know how much base you added to your unknown acid. So you have a known base. In this case, in the case that you have a known base and you're adding that to an unknown acid to neutralize it, then you have to do your calculations. So the first thing you know now is that you know the volume of base you use to get the endpoint. That's the purpose of your burette. So the burette is telling you how much volume of your known base you added. So this is from the burette during lab. From this volume, you know the concentration of your base, you know the volume, so now you can do the calculation to get the moles of base you use to get to the endpoint. Okay, and so you convert by multiplying the volume by the moles, right? Okay. Um, So you use molarity to get to the number of moles. So sorry, not volume times moles, but you go from the volume to the moles using the molarity of the known base. And then you're going to get the moles of acid in the unknown solution because at the end point, assuming you did your job right or you did a good job in titrating, the number of moles of acid is equal to the moles of base. And then at this point, now that you know the moles of acid, you can figure out the concentration of the acid because you already know the volume of the acid that you used, right? That's a known because you're going to use a pipette to pipette a certain volume to your Erlenmeyer flask. So you know the volume of acid you added. And so now you know the moles of acid that was originally in the titration or and then you can use your molarity equation. So you know that molarity is moles over liters, and so you can calculate the concentration of your unknown acid. If you flip it, if you know the acid and you have an unknown base, well then you're going to titrate the unknown base. The unknown base is going to be in your Erlenmeyer flask, and your known acid is going to be in your burette. And so you titrate that way, and then when you get to the end point, you will now know how many moles of acid you had to use to titrate and neutralize the unknown base. So basically, it's the exact same calculations, but now you're just starting with a known acid. So you know that at the end of your titration, at the end point, you now have the volume of acid you use to get to the end point. And again, this is from the burette during lab. You now can calculate the moles of acid you use to get to the end point. And then that way you're going to use your molarities equal moles over liters. So you're going to multiply your volume in liters by the molarity to get moles. And then now you can calculate the moles of your unknown base, the moles of the base in your unknown solution, because again, at the end point, assuming that you did a good job in titrating, moles of acid is going to be equal to the moles of base. And again, because you know the moles of the because you know the volume of the unknown base in your Erlenmeyer flask, because you put it there, and now you know the moles of base, you can now use your molarity equation, molarity is equal moles over liters, to calculate the concentration of your unknown base. Okay, now here are some things to be careful of. So first, milliliters versus liters. You got to remember that we're measuring stuff in milliliters, but when you're calculating molarity, it has to be in liters. So make sure you're converting your volumes to the proper unit before you calculate the concentration. Second, make sure you pay attention to stoichiometry. Not everything is a 1-to-1 ratio, right? So make sure that you know is the ratio of acid or H plus the same as is the amount of H plus same as OH minus, meaning is the ratio 1-to-1, right? Um, for example, 1 mole of NaOH is going to be equal to 1 mole of OH minus, right? So 1 mole, it's a 1-to-1 ratio. 1 mole of NaOH is going to give 1 mole of OH minus, whereas 1 mole of calcium hydroxide, right, gives off 2 moles of hydroxide ion. So you got to pay attention to the stoichiometry, the mole ratios between the amount of base or acid you have compared to the amount of hydroxide ion produced or the amount of H plus ion produced. But on top of that, you also have to pay attention to the mole ratio between the base and the acid, right? Is the acid a polyprotic acid? Is it a monoprotic acid? Is your base a dibasic base, a monobasic base, right? Does it have one hydroxide? Does it have two? So those are the things you want to watch out for. And again, the endpoint and equivalence points are only identical if your titration is absolutely perfect, but this is never the case. You don't have, perfect titrations because there's always error in labs. So, um, so the endpoint is where you have a color change in the titration. Sorry about that. So the thing you want to keep in mind is that the end point and the equivalence point are not the same thing. They don't mean the same thing. So the end point of a titration is the point at which you get a color change with your indicator. Your indicator gives that color change. The equivalence point is the point in your titration where the number of moles of acid is equal to the number of moles of your base. And so that's going to be a distinction because they're not exactly lined up, necessarily lined up perfectly because of the error in your lab. But we try to pick an indicator that's going to change color that's going to match as closely as possible to the equivalence point. And so those are a few things to keep in mind. Okay, so that's it for this video. Thank you for tuning in. I appreciate you watching the video. If you like the video, please like, share, subscribe the video. Make sure that you subscribe to my channel, hit that notification bell, click all for all videos that you want to see, and also make a comment in the comment section. Ask me questions. I'd love to hear from you. Thanks for joining me, and have a great day.